My name is Salina. Today I'm going to be presenting on behalf of Forethought and talking about how we scaled our end-to-end machine learning platform using a modular approach. So I'm going to go through a brief introduction of Forethought, the company, and talk about the components of a sound ML infrastructure. Talk a little bit about the challenges of building an ML infrastructure that's scalable, and kind of dive deep into a case study of how we took a modular approach to replacing pretty much every component of our end-to-end ML infrastructure. Do a little recap of the key takeaways and some acknowledgements. So, quick introduction on Forethought, the company. So, what is Forethought? Our mission is to unlock human potential through AI. So we're an enterprise SaaS company offering a generative AI platform to streamline customer service. So at pretty much every stage of the support ticket lifecycle, we have products that use ML to automate the lifecycle. So this includes things like ticket resolution through our Solve chat widget, ticket routing, agent support, and optimizing workflows through autonomous agents. So where does machine learning come into play at Forethought? So ML is really the bread and butter of our business and product. We build per customer fine-tuned models, which means that the number of models that we need to train and build and manage will scale with the number of customers that we have. So having a scalable, cost-efficient, and resilient ML infrastructure is really critical to our business success. You can kind of see this diagram, our ML team organization on the right. So we have ML engineers that do experimentation, build the training and inference code. We have ML infrastructure and the core infra team that is building out the ML platform. And we have implementation engineers that use the ML platform to build production models that power our products that our end customers then use. So now that we've kind of established the importance of an ML infrastructure, let's go through kind of the key components. So at a very, very, very high level, these are the building blocks of an ML infrastructure. So we have data training and serving infrastructure that kind of lead into one another. We have ML monitoring on top of it, and we tie it all together with workflow automation. So this is at a high level, what the key components are. And I'm going to talk a little bit about how to scale and grow each component. So I basically made checklists for understanding how scalable each component is. I'm not going to go into each bullet point in depth in the interest of time. Feel free to take screenshots if you would like. For ML data infrastructure, we're basically talking about how we clean and prepare the data for training, feature engineering, validating the data and data sets. So some things to highlight here are automation, reproducibility, reusability of the feature data, versioning and lineage tracking of the features, and validating your feature data. For experimentation and training, this is how you build an efficient experimentation platform and use this to standardize your production training. So some things to highlight here are going to be automation, reproducibility of your experiments, tracking your experiments, configuring your experiments. So this is important for configuring what types of resources you need to run your experiments, especially if you're using GPUs. And CI/CD, CT, how you kind of test and deploy your training pipeline. Once you have trained your models, you're going to want to deploy your model to an endpoint and serve traffic to them. And some things to consider here, again, automation, configurability, managing the resources you need to serve the model, which might be different than the resources needed to actually train the model. Again, CI/CD, CT best practices, and extensibility, meaning how straightforward is it to introduce new model types or frameworks to your system. And lastly, machine learning model monitoring. This is really critical for understanding the performance of your models and of your system. And what you're really wanting to look for and like track are the performance metrics of your model, so data drift, and the system metrics, things like latency and resource utilization, how you are visualizing these metrics and alerting on them. And ultimately, the goal for ML monitoring is to introduce like automated retraining systems where you can trigger retraining your models if the performance drops beneath a certain threshold. So what are like kind of the challenges with scaling and automating ML infrastructures? There's obviously a lot to consider when building out an ML infrastructure. So what I have been kind of seeing is that building a scalable and reusable ML platform is often an afterthought in productionizing ML models. It's really easy to incur tech debt with ML systems. ML infrastructure often gets deprioritized in favor of addressing urgent business needs. So if you have workflows in place, even if they are really tedious and really manual and slow, it often seems a lot quicker and easier to just stick with these workflows rather than building out a whole new system and migrating to it because of that initial cost of building and migration, that initial lift. So another thing is ML ops is a relatively new field. So oftentimes companies, especially smaller companies with smaller teams, lack the resources or expertise to build out a solid ML infrastructure. And it's harder for these teams to proactively identify and foresee specific ML ops needs for their use cases and understand how exactly to address them. So a very common scenario, and one that was definitely the case previously at Forethought, is for ML ops to be ad hoc and decentralized, and there's no good way to reproduce these processes. So ML modelers, so like ML engineers or data scientists, are building and maintaining their own ML stacks, and they're hyper-specific to these individual use cases, and no way to like reuse these for additional use cases, and they're not automated workflows. I think at the core of the challenges with ML infrastructure, it's really because ML ops kind of rests in the middle of this three-circle Venn diagram between machine learning, DevOps, and data engineering, and that's where I see the biggest challenges with ML infrastructure. So on kind of the more DevOps side, figuring out how to manage and configure resources for both training and serving, particularly using large and expensive GPU resources, which are more and more in high demand these days. On more the data engineering side, managing feature data, ensuring and validating, maintaining high data quality. ML systems are highly data dependent, so you have to constantly be monitoring the data that you're using. And from the ML side, if you think about it, ML training and serving have kind of different and contradicting goals. For ML training, the goal is really to build highly accurate models. For serving, especially if you're doing, like real-time serving, the goal is to serve low latency, high throughput traffic. Then these two goals can be at odds with one another. So how do you identify that actual specific gaps in your system? I think some of the key pillars to think about are automation, reusability, reproducibility, and extensibility of your system. So here's a list of some things you might, kind of look at. So if your ML infrastructure has a lot of manual multi-step processes, this can be very time consuming. If for the same process, there's multiple ways to do the same thing, that can be something that you can think about consolidating or centralizing. If it's tedious to reuse any part of your life cycle, then you might have a problem with reproducibility in your system. And if it's unclear how to move from one part of your life cycle to the next, so for example, you've trained a model, but it's not really clear how to actually deploy your model, you might have some gaps you can fill with automation, or you might even just be missing some parts of the major ML infrastructure components. If there's no visibility into existing feature data or actions such as previous experiments or deployments, this might be something to address. for reproducibility. And if there's a big lift to support training or deploying new model types or frameworks, that means your system is not as extensible as it maybe could be. And one, I think, really major thing to look at is whether training and serving your models are costing lots of money. That can be something to maybe optimize in your system. So I'm going to go into a kind of case study of how we scaled our ML infrastructure at Forethought, and each component, how we did it. So our kind of V0 infrastructure was definitely workable in the sense that ML engineers were training and deploying models for production, but it was not very scalable, it was not very extensible, and it was costing us lots of money. So as you can see from this diagram, we were using GCP pretty much just for ML training. All of our other cloud infrastructure was on AWS. We didn't have CI/CD and versioning for our training and deploy pipelines. Model serving was done on Kubernetes. We didn't have a dedicated like ML serving platform, and it was very costly and resource wasteful, particularly with the GPU resources that we were using. And at pretty much every step of the ML lifecycle, there was a lot of ad hoc and manual work being done. So our approach, we took kind of a modular approach to build our rebuild our ML infrastructure. You can see this diagram of an MVP product illustration on the right. It's a little bit different because we weren't like building a product from scratch, but we kind of tried to maintain this idea of maintaining usability as we were swapping out each component. So what we did was reframe our infrastructure as modular, different but interacting components based on those 5 components that I introduced at the beginning. And for each component, identifying how the existing system worked and what the shortcomings were, using those shortcomings to identify the major goals of the new system or new component and what the gaps were between where we were and where we wanted to get. We then architected and built out each component and onboarded our stakeholders to the new systems, receive feedback from them and iterate as needed. And this was kind of the modular approach that we took. So I'm going to dive right into like the first component, which is the ML data infrastructure. So what we did was essentially build out a centralized feature store. So how did we identify the gaps with our existing system? So for more context, a lot of our models are language models that we train on support ticket data. So you can see in the diagram on the right, basically what the workflow looked like was previously was we would have engineers that would be pulling raw data from the data lake. They would then pull code for data transformations, and maybe they had existing transformation logic on their local machines and run these transformations on the raw data. This would then yield their individual data sets for their individual needs, and they would push these data sets to S3 where they could then use them for training. So this was really time consuming and error prone because all the transformation logic was decentralized. It was really difficult to know for each data set what transformations were being performed, and there was no source of existing features. So that means data might be unnecessarily reprocessed since these features are not stored. And to give kind of an example of some of the transformations that needed to happen, we would trim text, and a lot of this logic for trimming was client-specific, join different tables, aggregate and map columns. So some of the mappings for new columns would involve calling machine learning models as well. So our solution was basically automating this process of data transformation or data cleaning and create kind of like the beginnings of a feature store. So we built a dedicated data cleaning pipeline that incrementally processes raw data and updates a centralized feature source. So the data, it lives in S3 and Hootie tables as Parquet files. And we use a PySpark job running on AWS EMR to perform the transformations. This job is orchestrated on Dagster, our orchestration platform. And essentially, this job is run on a schedule daily and submits a Kubernetes EMR job run to run this PySpark job. And our end users can then access the centralized features via dbt views that we created over the process data, and they could query this data from Metabase using AWS Athena. So what are kind of like the results and findings from our migration? So essentially, we were able to centralize our feature engineering logic and our feature data storage. We automated the like core feature engineering steps of the data cleaning. So our engineers now don't have to do manual processing. When they want to train new models, they don't have to like pull raw data and transform it. We created a multi-purpose feature source. So these features are now reusable and transparent for anyone to use. There's no more like repeated data processing. And all the data cleaning runs, as well as the configurations used for the runs, are tracked. So you know, like for the data and the clean data source, you know like what transformation logic was used for them. And now, if a user wants to train a new model, creating a data set is as simple as querying the clean data source using SQL and exporting it to a data set. I want to like highlight some of the challenges that we ran into when building out this centralized feature source. So the biggest challenges were definitely data scale. So we had hundreds and millions of rows in our like tables that we were processing. So we had to do a lot of like Spark and SQL tuning to be able to process this much data, and pipeline flexibility. So this goes into like the extensibility of our system, allowing for backfills, allowing for changes to the transformation logic, and being able to track those transformations. These were all things that we had to like kind of proactively consider when we were architecting the system. For our moving on to training platform migration, so identifying the gaps here, as I kind of alluded to earlier, our previous ML training architecture was primarily done on AI platform, which is now, I think, called Vertex in GCP. So the reason why we did this is because we wanted to utilize TPU resources, and training here in GCP was done in notebooks and also on AI platform. So what the workflow would look like was the data sets were in S3, and then we would have to push them to GCP. And then at this point, they would be used for training. And then once the model artifacts were trained, we would push these artifacts back to S3. So there was a lot of steps happening in this pipeline. There was also no CI/CD for the training code and pipelines, and a lot of inconsistencies between experimentation and production training. Experimentation was mostly done ad hoc in these Jupyter notebooks, and this would result in like the production training code becoming inconsistent with experimentation. So we really wanted to move off GCP and incorporate CI/CD best practices. We ended up evaluating several different platforms for training. Some of the platforms we evaluated are SageMaker, Kubeflow, and Databricks. Happy to talk a little bit more about what our evaluation process was for these platforms if people are interested. But we eventually settled on SageMaker. And what we did was create a new GitHub code repository to house all of our machine learning code. We called it MLDS for Machine Learning Data Science. And this code repository is organized into different experiment types. MLDS is built heavily on Hydra, which is a YAML-based configuration tool that allows multi-experiment runs, hierarchies, multi-source composition. So what this means is that our ML engineers can iterate quickly by running multiple experiments with different configurations, submit these experiments to SageMaker using pretty much just command line configuration. And then there's a script in MLDS that basically submits a SageMaker training job, and we built the script in a way that the training code that runs when you submit experiments locally is going to be the same as if you submit it to the cloud. So there's that kind of like consistency between experimentation and production training. And with MLDS, we track all of our experiments through ML flows. So in that way, we can track, all of the parameters for training, the data sets used, etc. And you can see like an example of how we do the job submissions with Hydra configurations on the left-hand side. So what are some of the results with our training platform migration? Our new workflow, as you can see on the right, it's kind of held together with MLDS, which is our centralized code repo. So our ML engineers can locally submit experiments through MLDS, and these will submit SageMaker training jobs, and these will all be tracked with MLflow. MLDS we have GitHub Actions that will build production image of MLDS that can be used by our implementation engineers to train their production models. So in this way, we have CI/CD and CT built into our training platform. We have really rapid iteration for experimentation. Experiments can be run directly from the command line with dynamic configurations in the same way that production training is run. And this way we have consistent logic between the two. Later on, I will kind of walk through how this production training image is used in our orchestrated pipelines for production. So moving on to our serving platform migration, so our serving infrastructure. We definitely had quite a few gaps to fill here. As mentioned earlier, our models were served on Kubernetes with EKS. So the way that we had it set up was that there was one endpoint per model for inference, and our deploy logic was spread across 3 different code repositories. So it was very difficult to manage. We had to manage EKS ourselves. And in order to attempt to share GPU resources, we would set rigid memory fractions for our models. And if we allocated too little memory, then we would risk OOMs. If we allocated too much, which is what we tended to do because OOMs are bad, we would end up wasting GPU resources and lead to higher cost of hosting. So in addition, we had some models, in particular our classification models that were being served on GPUs, but probably could be optimized to be served on smaller resources or even CPUs. So again, we went through a evaluation period for frameworks to migrate to and settled on SageMaker. In particular, they had 2 offerings that we were really interested in. Serverless and multi-model endpoints. So essentially, SageMaker serverless, the way that works is you pay for compute capacity for inference and the data that you're processing. You could scale down to 0, essentially. You might run into cold start times, but there's ways around this, like using provisioned concurrency for a small premium. And this is ideal for models that only require CPU or have uneven traffic. Multi-model endpoints allows you to share container and GPU resources among multiple models. And SageMaker handles all the model loading and unloading, which is essentially what we were doing before. So this is more ideal for models that require partial GPU resources and expect near real-time latency, but can handle a cold start if the model has not been loaded in yet. So I'm going to talk a little bit about optimizing our models for serverless hosting. Our classification models we identified as maybe being able to optimize. So we used a couple of techniques, including distillation, quantization, domain adaptation. And we were able to significantly reduce more than half our model size and reduce significantly the latency of serving these models on CPUs. And at this point, this kind of opened the doors to being able to use SageMaker serverless to host these models at like a tiny fraction of the costs that we were using before. For our models that did still need GPU resources or needed more real-time latency and couldn't really handle the serverless cold start, what we did was convert these models to be able to be served on Triton. And this is because SageMaker multi-model endpoints uses the Triton inference server, which has specific model format and file structure requirements. And in particular, we use Triton ensemble models to include pre and post-processing steps and Triton Python backend models for more custom logic, such as loops and cached calls for our sequence-to-sequence models. And the last thing that we kind of did as part of our serving platform migration was build out a centralized model management layer with several routes. And this kind of acts as a proxy for any model management that needs to happen, whether it's being called by our orchestration platform or internal tooling. And maybe most importantly, this serves as an inference proxy between our backend services and actual model inference with SageMaker. And it handles all the logic for calling SageMaker inference. So kind of as a result of this, we were able to really significantly reduce our costs of model hosting. We were able to reduce the number of OOMs that we were seeing and centralize all of our model management and inference layer, essentially like creating an ML gateway for our models. And you can kind of see like the architecture on the right-hand side. We also wrote a joint blog post with AWS. I'll drop the link to the blog post in case anyone is interested. I'm sorry, I didn't realize there were questions. Happy to answer closer to the end of the talk. With orchestration, this is kind of falls in the category of workflow automation, and essentially our train and deploy pipelines we had built on Spinnaker previously. And the pipelines were defined in JSON, and it's all UI based. So there was not a lot of visibility into how exactly the pipelines were built and how they were being changed. And DevOps and infrastructure were kind of the gatekeepers of orchestration. We turned to Daxter, which is an open source Python-based orchestration platform with really great observability and monitoring capabilities. And I know we're a little bit short on time, so I'll go like really quickly through this, but essentially we created Daxter jobs for feature engineering pipeline orchestration, training pipeline orchestration, which includes steps to split our training data sets and submit our SageMaker training jobs using our production training image, and deployment pipeline orchestration. And deploying our models to SageMaker endpoints. So the really nice thing about this is that the workflow didn't change really for the end users, and even the deployment and training code didn't really change. We essentially just got the webhooks that were being called. And users can now use the Daxter UI to visualize and debug their pipeline runs. And also because Daxter is Python-based, it's a lot more straightforward for users to add or update their pipelines. It doesn't really require any additional infrastructure knowledge. And now our training, data cleaning, and model deployment pipelines are all fully automated on Daxter. With model monitoring, as mentioned, we created a model serving API proxy layer, kind of like a model gateway, where we were tracking our system metrics and visualizing them in Grafana, but we weren't really tracking any data or prediction drift. So we were really slow to know when our models weren't performing, sometimes even just finding out from our customers if the models weren't performing well. So the goal was really to allow our stakeholders to see how well their models were performing in production and how it was changing over time. We essentially created ways to visualize our model prediction metrics and trends over time. And the nice thing about our solution was that it was powered by metadata tracking, meaning that as long as product teams were sending the metadata via Prometheus, like the visualizations would be there. So they were kind of getting that for free. So what were some of the metrics that we were calculating and tracking? So maybe the most important thing, the kind of baseline training data distribution that we were tracking and visualizing for each experiment, as well as like the accuracy and prediction rate, weekly trends, and the accuracy counts over weeks, and comparing the model predictions to the ground truth labels. And so the kind of architecture for model monitoring, we were tracking all of our predictions and their metadata via our model serving API, writing the predictions, ground truth, and metadata to the data lake. And this was also coming from our backend services, building dbt views over our predictions and ground truth data tables, and using Metabase and Athena to query these metrics and create visualizations. And then we would embed these visualizations into our internal tooling in Retool so our end users could use them. I think we're a little bit over time. I will keep going because I think we still have some viewers here. So kind of a recap of the full architecture. So we really try to build out every component. So data infrastructure, is a lot more automated with our Spark job and our centralized feature source. Our training infrastructure now is built on top of the SageMaker platform, and we also incorporated CI/CD CT on top of our ML training code with MLDS. Our serving infrastructure is also built kind of on top of the AWS SageMaker platform using serverless and multi-model endpoints. And we also have this model serving API proxy layer for inference and model management. We orchestrate everything using Dagster, which connects to our internal tooling with Retool. And then for ML monitoring, we now track all the predictions and their metadata in the data lake and visualize these in our internal tooling. So what are some of the things that we want to look at for our kind of V2? So extending and maturing our infrastructure some more. So we want to introduce automatic retraining when model performance drops. So this is really tied to model monitoring and also our training pipelines. At the moment, we do have engineers doing this, but it's more ad hoc and it's not kind of built into our platform. The challenge here is really being able to identify the correct metrics and thresholds to use. And for building this into our platform, having a way for users to specify these metrics in a way that's kind of extensible. Automating feature data validation during feature engineering and alerting on data validation. So the challenge that I see here is really creating a high-level abstraction for users to define these data validation specifications and then kind of translating them in our system to how we actually validate the data. We want to continue to abstract and modularize our training and deploy logic and make our system even more extensible for new model types and new frameworks. Challenge here, I think, is really just managing technical debt. When we build systems, there's always going to be some assumptions made and kind of going back and making it more abstract and modular. And lastly, supporting training and serving larger models on larger resources. And this is especially important as we continue to kind of explore LLMs for our product use cases. The challenge here, I think, is resource scarcity and the high costs of resources. One thing that we're currently looking into is using SageMaker Inferentia as an option to hosting these larger models. So some of the key takeaways from this, understanding the core components of an ML infrastructure, as well as the core kind of like pillars of a scalable ML infrastructure. So these are things like automation, making sure your pipelines are orchestrated, reusability, making sure your ML code is centralized and modularized, reproducibility, making sure all your experiments and data processing are tracked and versioned, and extensibility. So making sure your ML code is abstracted and that you're avoiding any like defaults or assumptions. As far as being able to identify gaps in your system, what we would kind of propose would be deep diving into each component, see where you can strengthen the above pillars. You can start with the previous checklists that were earlier in this presentation. And kind of a recap of our case study. For data infrastructure, we created a centralized feature engineering pipeline and feature source using Spark. For our training infrastructure, we migrated our training infrastructure from AI platform to SageMaker and centralized the code in one repository and introduced CI/CD best practices. We migrated our serving infrastructure from Kubernetes to SageMaker serverless and multi-model endpoints, which resulted in really great cost reduction. We calculated and visualized data drift using dbt and Metabase. And we introduced a new orchestration platform using Dagster for all of our ML pipelines. I want to give quick acknowledgements to everyone who helped kind of build the ML infrastructure at Forethought. Jad, Yi, the core teams, the ML engineering team, all the engineering teams at Forethought, our AWS partners, MLOps World, Generative AI World for hosting this, and everyone who attended this talk. Feel free to reach out. Here's my contact information and my LinkedIn. I'm going to take a look at the chat to kind of address some of the questions. So, did you use any third-party tooling for your feature store or build your own? We pretty much used just the AWS infrastructure. So we used EMR to run Spark jobs, and we didn't really use any third-party tooling outside of that. And I guess we use Metabase for the visualization and querying of the features. How do you manage feature version, e.g. feature data changes over time? That's a great question. We don't really version the specific features right now, which is why I was careful in my presentation to call it like a feature source instead of like a real feature store. We keep track of the transformation versions for the feature data, but the individual features are not at the moment versioned. Would love to hear your evaluation processes on these different platforms. Yeah, for sure. So there were three kind of like evaluation processes that we did. So there was the training, serving, and orchestration platforms. So for training, we were evaluating SageMaker, we were evaluating Kubeflow, and we were evaluating Databricks. So Kubeflow, we decided not to go with because of the fact that it's open source and would require a lot more infrastructure lift. Databricks, we decided not to go with because, so the whole reason why we wanted to kind of get off of GCP was largely in part because we were holding customer data in both AWS and GCP. And there's additional like data concerns for where you hold your data, and data privacy. So if we used Databricks, we would run into this kind of same issue where our data, our customers would have to like sign an additional, thing about their data being stored in Databricks, and just additional data compliance issues. And so SageMaker was kind of the best of both worlds in the sense that it would be a managed platform, so less infrastructure lift, and all of our data was already in AWS. For feature store, did you audit? Oh, sorry. Actually, I don't know if there's. I mean, there's also the serving platform evaluation. So for that we were considering SageMaker, and Ray, and Selden. So Ray Serve at the time was a little bit too green for us. We wanted a platform that had been around for a little bit longer, even though we were really interested in the way that their platform worked. And then with Selden, it was kind of the same thing. It would require a lot more infrastructure lift, similar to our evaluation with Kubeflow. And for the orchestration platform evaluations, we were looking at Dagster and managed Airflow in AWS. I don't know how many of you have used Airflow before. I and a lot of people at Forethought found that writing DAGs in Airflow was, kind of convoluted and not super straightforward. Definitely not compared to the way that you write jobs and ops in Dagster. And after evaluating the kind of infrastructure lift for using Dagster, we determined that even though it's open source and even though we're a pretty lean team, the lift was actually not that bad. So that's why we decided to go with Dagster. So that's kind of like high level evaluation processes for the different platforms. For the feature store, did you automate business transformation rules or just the basic cleaning rules? Are the rules different for various departments? How did you handle this for the feature store? That's a really good question. So basically, we started with like an MVP of the feature, the feature engineering pipeline. So we kind of consolidated the most used transformations. So that was really like trimming certain joins and mappings of the columns, and incorporated that into our first version. So this kind of fit the bill for several different teams or departments that were doing their own transformations, and this is a good point. It's definitely something that we want to continue making more and more extensible. What made you pick SageMaker over Kubeflow? Okay, I think I talked about that a little bit. Reason to choose MLflow over options like Comet ML, TensorBoard. So yeah, actually, so with the way that MLDS is built, we also do track with TensorBoard. I don't think we use Comet ML. We use both MLflow and TensorBoard. I kind of called out MLflow because I think our ML engineers use that a little bit more in practice for tracking the experiments. I think they serve a little bit different purposes as well. But yes, we essentially abstract out different loggers that we can use. So we log to MLflow. We also log to TensorBoard. Okay. And for ground truth, did you have to manually predict production data to come up with the data set to monitor the model? Did you have to manually predict production data to come up with the data set to monitor the model? Not sure if I fully understand the question. For model monitoring, the ground truth, we just essentially, like, depending on the product, there's ways to like keep track of what like the ground truth is. So for example, like ticket routing, if if it was actually routed to a different category than what the model had predicted. And this is like the kind of like ground truth data we would use. We didn't like manually predict any other data to monitor the model. Where do you guys keep all the versions stored for each component? Depends on which components. So I mean, like for example, like um, the the training, like the training pipeline, kind of like production training pipeline. Those are like versioned in the name of the image. I don't know if there's something like more specific that you're kind of referring to or asking about. I'm happy to answer. Did you consider dbt for the data transformation pipeline? Great question. Yes, we did consider dbt for the data transformation pipeline, but we ended up feeling like Spark would be more efficient and like more flexible with capturing the kind of transformations that we needed to do. Some of the steps that we needed to account for were like calling out to a separate API to trim text, and just like more specific like Python logic that we wanted to, or not Python logic, but just more specific logic that we wanted to incorporate. So we didn't feel like dbt would be able to cover all of our use cases in that sense. Thank you for all the great questions. Not sure if there's anything else, but yeah, happy to. Maybe meant for like each training run, for example, data transformation. Are these all logged? Yeah. So yeah, all the training runs are versioned, and when we like when we train a new model, essentially we have like using the model serving API kind of like model management layer, it will like auto increment the versions for you when you want to like train a new version of a model, for example. And for data transformations, we keep track of like the transformation logic version. So for example, like the trimmer API call that I was referring to, that version is like stored with each data row. So when you kind of like when the transformations are run, for each data row like what version of the trimmer is being used, and that kind of goes. It's the same for like any other like transformation that's happening in that cleaning pipeline. We're keeping track of what like version of transformation logic we're using. Hopefully that answers your question. Any other questions? Well, I think that might be it. Thank you so much, everyone, for attending. I want to really quickly drop my contact info. How did you maintain the learned parameters of scaled values in training pipelines to reuse in the inference pipeline? How did you? Thank you so much. How did you maintain the learned params of scaled values in the training pipelines to reuse in the inference pipeline? Not fully sure if I completely understand your question. If you're talking about like, the parameters that we're tracking in like from training, like experimentation, or submitting training jobs, we do track all of that with MLflow. That's all tracked with MLflow loggers. I don't think we have a way to like. I'm trying to think. I'm not sure if there is a process to like automatically reuse these values in inference, like as far as hyperparameters that are being logged or anything like that. But we like as far as like tracking the parameters learned and used in training, like we do all of that with ML flow essentially. Yeah. Any other questions? Yeah. Thank you for asking. Cool. I'll drop my contact in case anyone wants to reach out. And yeah, thank you so much, everyone, for attending this talk. I'll stay on for a couple more minutes in case anyone has any other remaining questions.